Okay. So we have learned about three kinds of reactions now. A single replacement, double replacement with the subcategory of acid-base. So that's three kinds of reactions. So here we're going to review a little bit again. Single replacement. Single replacement is when you have an element by itself that's going to replace the part of a compound it's like. So the A, if it's A as a metal, it's going to replace B, which will be a metal ion, and you get a C plus B, gets the B by itself. Or if A is a halogen, then it'll replace the C part, and you end up with a B and the halogen by itself. Either one of those is a general type of equation for single replacement. Okay? Then we learned about double replacement. Alright? In double replacement, you've got two different two-part compounds. A front part and a back part, a front part and a back part. And in double replacement, the front part of this compound joins up with the back of this one. And the front part of this joins up with the back of that one. And the front parts always stay in the front. So A is going to join with D, and A is going to be in front because the front parts stay the front parts. C is going to join with B. C will be in the front because the front parts always stay in the front. Okay, so that's double replacement. Then we have a subcategory under double replacement we called acid-base, okay, or neutralization. And in that case, you always have an acid. We symbolize that as HA because all acids have hydrogen on the front, at least in the Arrhenius definition we use at this point in time in this class. And the bases in the Arrhenius definition always have hydroxide on the back. So this B stands for any cation with a hydroxide. The A stands for any anion with a hydrogen on the front. And this is the double replacement, so the front part's going to go with the back part of this. The front part of this goes with the back part of that. And then I gave you some definitions that had to do with this as well. Some names. This is some kind of acid. This is some kind of base. This is going to be water here, and that's going to be a liquid. When we're running an acid-base reaction, you always produce water in liquid form. And then in an acid-base reaction using Arrhenius acids and bases, in addition to water, you always produce a salt. This is a new definition of a salt for you. The product of an Arrhenius acid-base reaction, other than water, is a salt. Okay? So we've done three kinds of reactions. All right, we're going to move on now to what is called combustion. All right, now, combustion reactions cover a large, broad category. We're going to simplify it down to only one kind of combustion reaction. Okay? It's going to be very simple, and it should be the simplest one of all to classify and predict products for, because the products are always exactly the same. All right? In a combustion reaction, you always have some kind of hydrocarbon. At least in this class, the only ones we're going to look at are some kind of hydrocarbon. Hydrocarbons are made of carbon atoms and hydrogen atoms. What you don't know when you start this anyway is what kind of carbon atoms or what kind of hydrogen atoms you're going to be using. So I'm going to put an X here and a Y because we don't know how many carbons. I said what kind of carbon. I mean how many carbons or how many hydrogens. Could be any number of them. Could be 1 here and 4 here. Could be 2 here and 6 here. Okay. Could be 12 here and 26 here. Okay. But we're always going to have a hydrocarbon to start with. Okay. Now what you also don't know, because of some factors that are a little beyond the scope of the class, is going to be what physical state the hydrocarbon is going to be in. Okay? So let's make that a Z here. All right? We don't know what physical state it's going to be in. I will tell you this, that Z is a gas if X is less than 5. Z is a gas if X is less than 5. Okay? Z is going to be a liquid, liquid, if X is, well, let's do it this way. X is, 5. Let's see, it's going to be 5 is greater than X, and X is less than 15. Then Z is going to be a solid if X is greater than 15. Okay? Now that's not really always true, but just to make it simple for you, okay, it's close. We're going to use 5 and 15, okay? Fair enough? Kind of like the 0.5 and the 1.5 we use for the break points when we're doing polarity. All right, just going to kind of keep it a little bit simple for you. All right, now, in a combustion reaction, this hydrocarbon is always going to react with oxygen. And oxygen in the air is always O subscript 2. And oxygen in the air is always a gas. Okay? So hydrocarbon and oxygen, and you always produce the same products. You always produce carbon dioxide gas, and steam. Okay? So if you see a hydrocarbon and oxygen, it's a combustion reaction. And you can always break the products because they're exactly the same. Carbon dioxide and water. That seems simple enough. And you can, all right, so let's try one and see how we do. You got a question? This is atmospheric oxygen. The kind you have that you breathe in. This is carbon dioxide gas. And this is water, and it's actually not just any water, it's steam. So it's water in the gas form. Okay? Alright, so here's our practice problem we're going to start with. Okay. So what class of compound is this? Okay, that's the physical state of the compound. Yeah, we could say it's a gas, you're right. But what category does this compound fit into? Is it a salt? Is it a covalent molecule? It is a covalent molecule, but in this case we also want to know that it's a hydrocarbon. Okay? If we react to hydrocarbon and oxygen, what is the classification of this equation? Okay? All right, we're going to classify it as combustion. If it's a combustion reaction, what are the products going to be? Well, there's water, it's just gaseous steam. Okay? So we predicted the products. Now we're left to balance the equation.
What are like real life examples of this? Like combustion?
Well, this is ethane. How about burning propane?
Same thing, propane?
Yeah. Same thing. Yeah. Yeah. How about gasoline? Gasoline is you could assume gasoline to be octane. Octane burning in oxygen. You get.
How come we can't see steam off propane? Like,
Huh?
if you throw propane in a grill, how come you can't see steam?
Because it's a gas. Because steam is not visible. You can't see steam.
In the shower it is.
No, what you see in the shower are condensation of the steam into water droplets.
No, not it. Like, steam from
What about when you're boiling water?
Yeah.
Huh?
What about when you're boiling water? That's steam.
No, but yeah, there is steam, but you don't see the steam. You see the condensation of the steam into tiny water droplets, like a cloud or like fog.
My whole life is a lie.
Steam is invisible, is virtually invisible. Well, you don't actually see the steam. You see evidence of the steam, so there's circumstantial evidence that steam is there, because what you see is the condensation of the water molecules. So the steam is at 100 degrees or above, 100 degrees C or above, and you can't see it. But when it rises above that boiling water, then it encounters the air above it, which is much lower than 100 degrees. So it cools off that steam, and those little tiny, those individual molecules of water then want to collect together in those little tiny droplets, and that's what you see.
What about in the shower? Because I want to take him to the shower.
Same thing. There is a lot of, because the water's warmer in the shower, water evaporates a lot faster. Okay? And those evaporated molecules then condense into tiny droplets that you can see. Okay? That's why your mirror gets wet. Alright? It's also condensing on the mirror. Alright? Okay. Now, let's balance the equation. You can balance the equation? Can you balance the equation? Everybody balance the equation. You can balance the equation. You might not want to. You might prefer to be lazy, but I won't let you. Balance the equation.